Hello, in this lecture we will talk about the limit of a sequence. A sequence is a set of numbers, and the sequence can be finite, like this sequence 157 that contains only 3 terms, and the sequence could be also infinite, like the sequence, like the set of the natural numbers that contains infinite terms. And the limit of a sequence is the value that the terms of the sequence tend to. Okay, so we write down that the limit lim is abbreviation for limit. The limit of sequence n is the index of the sequence, and a is the value of the term that its index in n is n. Again, n is the index of the sequence, and a is the value of the term that its sequence is n. So the limit of sequence an when n tends to infinity, that is the way that we will write down that the limit of sequence an when n tends to infinity. So if such a limit exists, for example, if the limit of sequence an when n tends to infinity is equals to L, and L belongs to the real numbers, L could be any real number. So in this case, the limit of the sequence an when n tends to infinity exists. Then we will call to sequence an a convergent sequence. Okay, so an will be defined as convergent sequence. And if the limit of sequence Bn doesn't exist, then sequence Bn will be defined as divergent sequence. If a sequence has a limit, it will have only one limit. That is to say, a sequence that has two limits doesn't have a limit at all. It is a divergent sequence. Actually, the limit of a sequence is said to be the fundamental notion on which the whole of mathematical analysis ultimately rests. So, what is the definition on the limit of a sequence. Actually, a number L is the limit of sequence AN when n tends to infinity if the numbers in the sequence become closer and closer to L. Okay? So only if the numbers of the sequence AN become closer and closer to L and not to any other number, we'll say that the limit of sequence AN when n tends to infinity is equals to L. So only if the terms of the sequence are becoming closer and closer to L, then the limit of sequence AN will be equal to L. Okay? Again, L is the limit of sequence AN when n tends to infinity. That is the first way to write down this thing. The second way to write down the same thing is AN with the right arrow is equal to L. So here I presented to you two methods to write down that the limit of sequence AN when n tends to infinity is equals to L. Okay? So only if the following condition holds, the limit of sequence AN when n tends to infinity will be equal to L. And the condition is as follows. For each real number epsilon that is greater than 0, there exists a natural number that is capital N, such that for every natural number n that is greater than capital N, we will get that the absolute value of AN minus L is less than epsilon. So only if this condition holds, we say that the limit of sequence AN when n tends to infinity is equals to L. I'll repeat on the condition that must hold. For every epsilon that belongs to the real numbers and it is greater than 0, that is to say epsilon is a positive number, as small as we would like, there exists the natural number capital N. So for any n that is also greater than capital N, n also belongs to the natural number. So for any n that is greater than capital N, we will get that the absolute value of AN minus L is less than epsilon. So only if this condition holds, we can say that the limit of sequence AN when n tends to infinity is equals to L. Actually, in this lecture we are talking only about sequences that consist of infinite terms, like the sequence of the natural numbers that consist of infinite terms. Okay? So what is the meaning of this condition that must hold? The meaning of this condition is that the terms of sequence AN are close to the limit L up to epsilon. So if the limit of sequence AN is equals to L, so L is at this point, then the environment of L starts from this point that is actually L minus epsilon and ends at this point that is L plus epsilon. So those two brackets this is the environment. So between those two brackets we have the environment of the limit L. I repeat again, the environment of L starts from this point L minus epsilon, and the point itself L minus epsilon is not included in the environment, and ends at this point that is L plus epsilon, and the point L plus epsilon itself is not included. Okay? So this is the environment of L, and you can see that each term that is located inside this environment, no matter where it is, that is to say each term of the sequence that is located inside those two brackets, it is actually far away from the limit L. The distance of any term from the limit L is less than epsilon. Okay? No matter where the term is located, every term that is located inside this limit is the distance of every term inside those two brackets. The distance of every term from the limit L is less than epsilon. So epsilon is the radius of the limit. Is the radius of the limit L. So in order that sequence will have a limit, actually most of its terms must be located inside those two brackets. Until the index n, we have fixed the number of terms. So until the index n, we have fixed numbers of terms that are not located inside those two brackets, but from the index n onwards, we have infinite terms of sequence AN that are located inside these brackets. Why? Because from the index L until the index plus infinity, we have infinite terms. And because of the fact that we have infinite terms of sequence AN that are located inside those two brackets, that is to say they are located inside the environment of L. That is the reason that the limit of sequence AN when n tends to infinity is equals to L. Okay? So symbolically, we can write down this condition that must hold in order that the limit of sequence AN will be equal to L when n tends to infinity as follows. For any epsilon that belongs to the real numbers and it is a positive number, it is greater than 0, there exists, this is the sign of exist, capital N that belongs to the natural numbers, and for N that is also belongs to the natural numbers, for N that belongs to the natural numbers, or for any N that is greater than capital N, we will get that the absolute value of AN minus the limit L is less than epsilon. Okay, that is how we write out symbolically that that condition must hold. So this condition must hold in order that the limit of sequence AN when n tends to infinity will be equal to L. Okay? I repeat again that sequence AN converges to the limit L, and therefore sequence AN is defined as convergent sequence, and L must be its only limit. In order the sequence AN will have a limit, L must be its only limit. Otherwise, if sequence AN has more than one limit, it doesn't have a limit at all. That is to say, if sequence AN has more than one limit, it is a divergent sequence. So in the next step, I will present to you an example of a sequence that its limit when n tends to infinity is equals to 0. So here we will have to prove that the limit of sequence AN equals to 1 over n when n tends to infinity is equals to 0. So the sequence is AN equals to 1 over n. That is to say, when the index n equals to 1, then A1 equals to 1 over 1. When the index n equals to 2, then A2 equals to 1 over 2. That is to say, the value of the term that its index is 2 is 1/2. When the index n equals to 3, then the value of the term that its index is 3 is 1 over 3, that is to say it is equals to 1/3. When the index n equals to 100, then the value of the theorem that its index is 100, it is equal to 1 over 100, etc., etc. And when the index n equals to n, then the value of the theorem will be equal to 1 over n. Okay, so those are the theorems of sequence an equals to 1 over n. It is very easy to see here that as the index n increases, the theorems of the sequence are getting closer and closer to 0. Why? Because when the index n equals to 1, then the value of the theorem is 1. When the index n equals to 2, then the value of the theorem is 1/2. When the index n equals to 3, then the value of the theorem is 1/3. When the index n equals to 100, then the value of the theorem is equals to 0.01. So you can see here that the terms of the sequence are getting closer to 0 as the index n increases. So you can assume that the limit of sequence an equals to 1 over n when n tends to infinity is equals to 0. So in order to prove that the limit of sequence an equals to 1 over n when n tends to infinity is equals to 0, we will prove that the condition that must hold indeed holds, and therefore the limit of this sequence is equals to 0. So the condition that must hold is as follows. So let epsilon be greater than 0, and let capital N be belongs to the natural numbers. So if capital N that we'll choose is big enough, so for every n that is also belongs to the natural numbers, for every n that is greater than capital N, we must get that the absolute value of 1 over n minus the limit 0 is less than epsilon. That is the condition that must hold in order that the limit of sequence an equals to 1 over n when n tends to infinity will be equal to 0. So we will actually prove that this condition indeed holds, and therefore the limit of this sequence is 0. So we have to prove that the absolute value of 1 over n minus 0 is less than epsilon. But when you subtract for anything 0, you change nothing. So you can cancel here 0, the 0, and this expression will be equal to the absolute value of 1 over n, because 0 changes nothing. So you can cancel it. And because of the fact that n is a natural number, that is to say it is a positive number, Therefore 1 over n is also a positive number. And we know that the absolute value of any positive number equals to the positive number itself. For example, the absolute value of 5 is equals to 5. Therefore, the absolute value of the positive number 1 over n is equals to 1 over n itself. So we can cancel the sign of the absolute value. So we have to prove that this expression is smaller than epsilon. That is to say, we must prove that the inequality 1 over n is less, that this inequality is true, that 1 over n is less than epsilon. Okay. So here we will multiply this inequality by n. And we will get that 1 is smaller than epsilon times n. Epsilon times n. Again, 1 is smaller than epsilon times n. I will write it again. 1 is smaller than epsilon times n. Here we will divide this inequality by epsilon, and we will get that 1 over epsilon is smaller than n, or n is greater than 1 over epsilon. That is to say, in order that this condition will be true, n must be greater than 1 over epsilon. And for that reason, we will choose capital N that is greater than 1 over epsilon, and for any n that is greater than capital N, we will get, so we know that n is greater than capital N. We can choose n that is greater than capital N, yes? But according to our selection, we choose capital N that is greater than 1 over epsilon. So from this inequality, we will conclude that n is greater than 1 over epsilon. So if we choose capital N that is greater than 1 over epsilon, then the condition that must hold, that is to say, this condition that must hold, indeed holds. Why? Because we found out here that n is greater than 1 over epsilon. Okay? And as I already mentioned before, we will choose n that is greater than capital N. That is to say, this inequality is true according to our selection. From the beginning, we will choose n that is greater than capital N, and for that reason, this inequality is true. Okay, so here we will divide this inequality by n, and we will get that 1 is greater than capital N over n. In the next step, we will divide this inequality by capital N, and we will get that 1 over capital N is greater than 1 over n. Or 1 over n is smaller than 1 over capital N. Okay? So, here we have to prove that the absolute value of 1 over n minus 0 is less than epsilon. But we have already proved that the absolute value of 1 over n minus 0 is equal to the absolute value of 1 over n. And we have already proved that the absolute value of 1 over n is equal to 1 over n. And we just right now proved that this inequality is true, that is to say 1 over n is smaller than 1 over capital N. Okay? So we'll focus on this expression 1 over capital N. So in the numerator we have 1, and in the denominator we have capital N. So if we leave the numerator as it is, that is to say, in the numerator we have 1, so we will leave 1 in the numerator, and we will substitute the denominator that is equal to capital N by 1 over epsilon. And according to our selection, here, according to our selection, we choose capital N that is greater than 1 over epsilon. Okay? Again, we choose capital N that is greater than 1 over epsilon. Okay? So we know that 1 over epsilon is smaller than capital N. 1 over epsilon is smaller than capital N. That is to say, we actually decrease the denominator here, and when you decrease the denominator, then the number itself will be greater. For example, if you have the expression 1 over 5, and you leave in the numerator 1, and you decrease the denominator from 5 to 4, then the number itself will be greater. That is to say, 1 over 4 is greater than 1 over 5. Okay? Therefore, when we decrease the denominator that is equal to capital N to 1 over epsilon, the number itself, that is to say the number itself that is 1 over epsilon, will be greater than 1 over capital N. Okay? Exactly like here, when we decrease the denominator from 5 to 4, then we get that the number itself, 1 over 4, is greater than 1 over 5. Therefore, 1 over epsilon will be greater than 1 over capital N. But what is the value of 1 over epsilon? It is equal to epsilon. So in conclusion, we found out that the absolute value of 1 over n minus the limit 0 is less than epsilon. That is to say, we proved that for any epsilon that is greater than 0, there exists a natural number that is capital N, and for we will choose natural number capital N that is greater than 1 over epsilon, and so we'll choose the natural number capital N that is greater than 1 over epsilon, and for any n that is greater than capital N, for any n that is greater than capital N, and we choose capital N that is greater than 1 over epsilon, we will get that the absolute value of 1 over n minus the limit 0 is less than epsilon. That is to say, the condition that must hold in order that the limit of the sequence an that is equal to 1 over n will be equal to 0 when n tends to infinity, the condition holds, and therefore the limit of the sequence an equals to 1 over n when n tends to infinity is indeed equals to 0. Okay? Repeat again, because of the fact that the condition that must hold in order that the limit of sequence an equals to 1 over n when n tends to infinity will be equal to 0, the condition that must hold holds, and therefore the limit of this sequence is indeed 0. Okay? So I'll repeat again on what we did here. We had to prove that the limit of sequence an that is equal to 1 over n when n tends to infinity is equal to 0. In order that the limit of sequence an that is equal to 1 over n when n tends to infinity will be equal to 0, we have to find out epsilon that is greater than 0, as small as we wish, and for n that belongs to the natural numbers, for n that is big enough, for capital N that is big enough, we'll get that for any n that is also belongs to the natural numbers and it is greater than capital N, we have to get that the absolute value of 1 over n minus the limit 0 is less than epsilon. So we know that the absolute value of 1 over n minus 0 is equals to the absolute value of 1 over n, and the absolute value of 1 over n is equals to 1 over n, and we have to prove that 1 over n is less than epsilon. We have to prove that this inequality is true. Okay, we actually multiplied this inequality by n, and we got that 1 is less than epsilon times n. Then we divided this inequality by epsilon, and we found out that n must be greater than 1 over epsilon in order that this condition will hold, in order that this condition will be true. Okay? So we choose capital N that is greater than 1 over epsilon, and because of the fact that capital N is greater than 1 over epsilon according to our selection, so for any n that is greater than capital N, and capital N is greater than 1 over epsilon according to our selection. So we get here that N is greater than 1 over epsilon. That is to say, if we choose capital N that is greater than 1 over epsilon, we will get that the condition that must hold, that is to say, the condition that must hold is N is greater than 1 over epsilon. Indeed, we will get that N is greater than 1 over epsilon. Okay? So, as I already mentioned before, we have the right to choose N that is greater than capital N. So, this inequality is true according to our selection. Therefore, we can divide this inequality by N, and we get here N over N is 1, so 1 is greater than capital N over N. Then we will divide this inequality by capital N, and we will get that 1 over capital N is greater than 1 over N. Okay, so this inequality is true because this inequality is true. Okay, this inequality is true according to our selection. So here we have already found out that the absolute value of 1 over n minus 0 equals to the absolute value of 1 over n. And the absolute value of 1 over n equals to 1 over n. And because of the fact that we have already found out that 1 over n is smaller than 1 over capital N, we can write it here, that 1 over n is smaller than 1 over capital N. And we choose capital N that is greater than 1 over epsilon. So here, if you have an expression and you leave the numerator as it is and you decrease the denominator, then the number itself will increase. For example, if we have the number 1 over 5, we will leave in the numerator we have 1, in the denominator we have 5. So if we leave the numerator as it is, that is to say, we will leave it as 1, exactly as we have here, and we decrease the denominator. In the denominator we have 5. If we decrease it to 4, from 5 to 4, then the number itself will be greater. That is to say, 1 over 4 is greater than 1 over 5. So when you decrease the denominator, the number itself will be greater. So here 1 over epsilon is smaller than capital N because we choose 1 over epsilon that is smaller than capital N. So here we decrease the denominator, therefore the number itself will be greater. That is to say, the number itself that is 1 over epsilon will be greater than the original number. So 1 over epsilon is epsilon. So actually prove that the absolute value of 1 over n minus 0 is less than epsilon. Okay? And therefore, we actually proved that the condition holds. Okay? If we choose capital N, if we select capital N that is greater than 1 over epsilon, then for any n that is greater than capital N, and capital N is greater than 1 over epsilon, then from this inequality we will get that n is greater than 1 over epsilon, and that is the condition that must hold in order that the limit of sequence an equals to 1 over n and n tends to infinity will be equal to 0. again, we prove that the condition holds. That is to say, n is greater than 1 over epsilon. Here, the condition that must hold is n must be greater than 1 over epsilon. And if we choose capital N that is greater than 1 over epsilon, we will get here that n is indeed greater than 1 over epsilon. That is to say, the condition holds. Okay, therefore, the limit of sequence an equals to 1 over n and n tends to infinity equals to 0. Okay. So we finished with the sequences that has a finite limit, and in the next step we'll talk about a sequences that has a limit in the broadest sense. So their limit is not finite but infinite. Okay, so we'll talk about sequences that have infinite limits. That is to say, they have a limit in the broadest sense. So a sequence an is said to tend to infinity, and we write down that the limit of sequence an when n tends to infinity will be equal to plus infinity. That is the first way to write down that the limit of sequence an is equal to plus infinity when n tends to infinity. The second way to write down the same thing is an with the right arrow equals to infinity. So the meaning of those two expressions are exactly the same. Both those two expressions, the meaning of those two expressions are the same. That is to say, the meaning is that the limit of sequence an when n tends to infinity is equals to plus infinity. Okay, so only if the following condition holds, we will say that the limit of sequence an when n tends to infinity will be equal to plus infinity. And the condition is as follows. For every real number k, as large as we want, there is a natural number capital N such that for every natural number n that is greater than capital N, we will get that an is greater than k. So only if this condition holds, we can say that the limit of sequence an when n tends to infinity equals to plus infinity. So here the limit is in the broadest sense. Okay? I'll repeat again on the condition that must hold in order that the limit of sequence an when n tends to infinity will be equal to plus infinity. For every k as large as we want, we have to find out capital N that belongs to the natural numbers. So for every n that is greater than capital N, and n is also belongs to the natural numbers, for every n that is greater than capital N, we will get that an is greater than k. that is to say, the terms of the sequence are eventually larger than any fixed k. Or you can say that after the index n, or after the index capital N, all the terms of sequence AN are bigger than k. Until the index n, we have fixed the terms that are not obeying the condition, but from the index n onwards, we have infinite terms. Why? Because from the index n until the index plus infinity, we have infinite terms of AN, and all of them are greater than the number k. That is to say, we have infinite terms of AN that are greater than the number k. And because of the fact that we have infinite terms of sequence AN that are greater than k, the limit of sequence AN when n tends to infinity will be equal to plus infinity. So here the limit is a limit in the broadest sense. Okay? So symbolically, we can write down the condition that must hold in order that the limit of sequence AN when n tends to infinity will be equal to plus infinity as follows. For every k that belongs to the real numbers, that is to say, k could be any real number as large as we want. There exists, this is the sign of exists, a natural number n, and natural number capital N. Again, capital N belongs to the natural numbers. So for n, it is also belongs to the natural numbers, or for any n that is greater than capital N, we will get that AN is greater than k. Okay? And because of the fact that until the index n we have fixed terms, and so maybe we will have fixed terms that are not obeying to this condition, but from the index n onwards, we have infinite terms of sequence AN that they are all greater than k. And because of the fact that we have infinite terms of sequence AN that are greater than the number k, for that reason you can say that the limit of sequence AN when n tends to infinity is equal to plus infinity. Okay? So in the next step I will give you an example of a sequence that its limit is equal to plus infinity. Okay? So we will prove that the limit of the set of the natural numbers, the natural numbers can be represented by the formula that AN equals to n. For example, when the index n equals to 1, then A1 equals to 1. When the index n equals to 2, then A2 equals to 2. The value of the term is 2. When the index n equals to 3, then A3 equals to 3, that is to say the value of the theorem is 3. When the index n equals to 100, then the value of the 100th theorem is 100, etc., etc. And when the index n equals to n, then the value of the term is n. So it is very easy to see that as the index n increases, the terms of the sequence are also increasing. Therefore, we can assume that the limit of the sequence an that is equals to n when n tends to infinity is equals to plus infinity. So that is our assumption, but we have to prove that the condition holds, and therefore the limit of sequence an equals to n is equals to plus infinity when n tends to infinity. So what is the condition that must hold? The condition that must hold is as follows. For every real number k, as large as we want, k belongs to the real numbers, there is a natural number capital N, and for any n that is greater than capital N, we will get that an is greater than k. So that is the condition that must hold in order that the limit of the set of the natural numbers will be equal to plus infinity when n tends to infinity. So in order that that condition will hold, we'll choose capital N that is equals to the integer value of k plus 1000 when it is rounded up. Okay? And for any n that is greater than capital N, and capital N itself, according to our selection, it is equals to the integer value of k plus 1000 when it is rounded up. We have to prove that an is greater than k. But according to the definition of the set of the natural numbers, we can represent the natural numbers according to this formula that an equals to n. a1 equals to 1, a2 equals to 2, a100 equals 100. So here we know that an equals to n. Okay? So we have this equality that is true, this inequality that is true according to our selection. First of all, an equals to n because that is the definition of the natural numbers. And n is greater than capital N according to our selection. We choose n that is greater than capital N. When we choose capital N, that is equal to the integer value of k plus 1000 when it is rounded up. That is to say, this inequality is true. Okay, so from this inequality, we can derive that an is greater then the absolute value, the integer value of k plus 1000 when it is rounded up. Okay? And if an is greater than the integer value of k plus 1000 when it is rounded up, let alone that an is greater than k. That is to say, we actually proved that if we select capital N, if we choose capital N that is greater, that is equals to the integer value of k plus 1000 when it is rounded up, then the condition will hold. That is to say, here we got that an is greater than k. Okay? And because of the fact that the condition that must hold holds, we actually proved that the limit of the set of the natural numbers, that is to say, the limit of the set of the natural numbers, that is an, that is equals to n when n tends to infinity, is indeed equals to plus infinity. Why? Because the condition that must hold holds. Okay? Similarly, we say that a sequence tends to minus infinity. That is to say, the limit of a sequence in the broadest sense is minus infinity, and we will write down that here the limit of sequence an when n tends to infinity will be equal to minus infinity. A second way, or a second method to write down the same thing is as follows. an with the right arrow equals to minus infinity. So those are the two methods to write down the same thing, that the limit of sequence an when n tends to infinity equals to minus infinity. So only if the following condition holds, we can say that the limit of sequence an when n tends to infinity equals to minus infinity. Here the limit is in the broadest sense. Okay? So the condition that must hold is as follows. For every real number k, there is a natural number capital N, such that for every natural number n that is greater than capital N, we will get that an is smaller than k. That is to say, the sequence terms are eventually smaller than any fixed k. I repeat on the condition that must hold, in order that the limit of sequence an when n tends to infinity will be equal to minus infinity. The condition that must hold is as follows. For every k as small as we would like, there exists the natural number n, and for every n that is greater than capital N is also belongs to the natural number, so for every n that is greater than capital N, we will get that an is smaller than k. That is to say, until the index n, we have fixed terms that are not obeyed to this condition, but from the index n onwards, we have infinite terms that are smaller than k. And because of the fact that in sequence an we have infinite terms that are smaller than k, for that reason the limit of sequence an when n tends to infinity will be equal to minus infinity. Again, here the limit is in the broadest sense. Okay, I'll repeat again, the condition that must hold is as follows. For every k as small as we would like, there exists the natural number n. So for every natural number n, there exists, for every k as small as we would like, there exists the natural number capital N. So for every natural number n that is greater than capital N, we will get that an is smaller than k. Again, because of the fact that from the index n onwards, we have infinite terms that are smaller than k, so we have infinite terms of sequence n that are smaller than the number k that is as small as we would like. For that reason, the limit of sequence an when n terms to infinity is equals to minus infinity. Why? Because the terms of sequence an are smaller than any small number. For that reason, the limit of sequence an in the broadest sense is equals to minus infinity. So symbolically, we can write down the condition that must hold in order that the limit of sequence an will be equal to minus infinity as follows. The condition that must hold is that for every k as small as we would like, and k belongs to the real numbers, there exists capital N, and capital N belongs to the real numbers. So for every natural number n belongs to the natural numbers, that is to say, for every n that is greater than capital N, we will get that an is smaller than k. Okay, I repeat again that from the index n onwards, we have infinite terms of sequence an that are smaller than k. That is the reason that the limit of sequence an in the broadest sense will be equal to minus infinity, because we have infinite terms that are smaller than k, that is any small number as we would like. Okay. So, in the next step, I will present to you the arithmetic of limits. So, if the limit of sequence an when n tends to infinity exists, And we also know that the limit of sequence Bn when n tends to infinity is also exists. So if the limits of sequences an and bn when n tends to infinity exists, then the following equations will be true. Equation number 1 is true. According to equation number 1, the limit of sequence an plus bn when n tends to infinity will be equal to the limit of sequence an when n tends to infinity plus the limit of sequence bn when n tends to infinity. Okay? Excellent. The meaning of equation number 1. In the left side of equation number 1, we actually will add the terms of sequences an and bn correspondingly. So in this way we will create a third sequence, and we will calculate the limit of the third sequence when n tends to infinity, and the result must be equal to the limit of sequence an when we will calculate it separately. We will calculate the limit of sequence bn separately. We will add the two limits, and the result must be equal to the limit of the third sequence that we created here when n tends to infinity. Okay, and we have also equation number 2 that is true. The limit of sequence an minus bn when n tends to infinity is equal to the limit of sequence an when n tends to infinity minus the limit of sequence bn when n tends to infinity. I will explain the meaning of equation number 2. In the left side of equation number 2, in the first step, we will actually subtract the terms of sequence bn from sequence an correspondingly. In this way, we create a third sequence, and if we calculate the limit of the third sequence that we created here when n tends to infinity, the result must be equal to the limit of sequence an when we will calculate it separately. We'll calculate the limit of sequence bn separately, then we will subtract the limit of sequence bn from the limit of sequence an, and the result that we will get, it must be equal to the limit of the third sequence that we created here, and n tends to infinity. Okay, we have also equation number 3 that is true. According to equation number 3, the limit of sequence c times an when n tends to infinity is equals to c times the limit of sequence an times the limit of sequence an when n tends to infinity. I will explain the meaning of equation number 3. In the left side of equation number 3, we have the sequence c times an. So we'll calculate directly the limit of sequence c times an when n tends to infinity, and the result must be equal to the limit of sequence an. So we calculate the limit of sequence an when n tends to infinity, and then we will multiply the result by c. C is any real number. C belongs to the real numbers. It could be any real number. Again, c times the limit of sequence an when n tends to infinity equals to the limit of sequence c times an when n tends to infinity. Here, we will calculate the limit of sequence c times an when n tends to infinity, and the result must be equal to the limit of sequence an when n tends to infinity when we calculate separately the limit of sequence an, and we'll multiply the result by c, and it is equals to the limit of sequence c times an when n tends to infinity. Okay. Equation number 4 is also true. The limit of sequence an times bn when n tends to infinity will be equal to the limit of sequence an when n tends to infinity times the limit of sequence bn when n tends to infinity. I explain the meaning of equation number 4. In the left side of equation number 4, here in the first step, we will multiply the terms of sequence an by the terms of sequence bn correspondingly. In this way, we actually created a third sequence, and then if we calculate the limit of the third sequence that we created here, the result must be equal to the limit of sequence an when we will calculate it separately. We will calculate the limit of sequence bn separately. Then we will multiply the two limits that we got by each other, and the result must be equal to the limit of the third sequence that we created here when n tends to infinity. Okay, and finally, we have also equation number 5 that is true. According to equation number 5, the limit of sequence an over bn when n tends to infinity equals to the limit of sequence an when n tends to infinity over the limit of sequence bn when n tends to infinity. Here, the limit of sequence bn when n tends to infinity must not equal to 0. I will explain the meaning of equation number 5. Here, we will create the first sequence by dividing the terms of sequence an by the terms of sequence bn correspondingly, and then we will calculate the limit of the first sequence that we created here when n tends to infinity. And the result must equal to the right side of equation number 5. What is the meaning of the right side of equation number 5? Here, first of all, we will calculate the limit of sequence an separately when n tends to infinity. We will calculate the limit of sequence bn when n tends to infinity separately. And then we will divide the two limits by each other. And the result must be equal to the limit of the third sequence that we created here when n tends to infinity. And here, because of the fact that the limit of sequence bn when n tends to infinity is in the denominator of this expression, and the denominator must not equal to 0. Therefore, here, the limit of sequence bn when n tends to infinity must not equal to 0, because it is not allowable to divide anything by 0. And finally, we have equation number 6. According to equation number 6, the limit of the sequence an to the power of p when n tends to infinity is equal to the limit of sequence an when n tends to infinity to the power of p. I will explain what is the meaning of equation number 6. Here, in the left side of equation number 6, we will actually calculate the limit of sequence an to the power of p when n tends to infinity in the right side of equation number 6, and the result must be equal to the right side of equation number 6. What is written in the right side? In the right side of equation number 6, we will calculate the limit of sequence an separately when n tends to infinity. After we will get the result, we will raise the result to the power of p, and the final result must be equal to the limit of sequence an to the power of p when n tends to infinity. Okay? So in the next step, I will summarize the lecture. So in this lecture, we're talking about the limit of a sequence. As I already mentioned in the beginning of the lecture, a sequence can be finite, like this sequence that consists of only 3 terms, and a sequence also could be infinite, like the set of the natural numbers that consist of infinite terms. So the limit of sequence an when n tends to infinity is equals to L. That is the way that we will write it down. Lim is a relation for limit. Sequence an, n is the index of the term, and a is the value of the term that its index is n. And we are talking about sequences that have infinite terms, that consist of infinite terms, and therefore we can talk about n that tends to infinity. Okay? Here, the limit that is equal to L, it is a finite number. That is to say, L belongs to the real numbers. Okay, so if a sequence has a limit, it will have only one limit. That is to say, if a sequence has two limits, it means that it doesn't have a limit at all. So if a sequence has a limit, it is defined as a convergent sequence. That is to say, if a sequence converges, it is defined as a convergent sequence. And the sequence that doesn't converge is defined as divergent sequence. Okay? So what is the definition of a limit of a sequence? As I already mentioned before, we will write down, this is the first way to write down that the limit of sequence n when n tends to infinity is equals to L. L belongs to the real numbers. L belongs to the real numbers. It could be any real number. A second way to write down the same thing is in this way, an with the right arrow, that is equal to L. Okay, those two expressions have the same meaning, that the limit of sequence n when n tends to infinity is equals to L. So only if the following condition holds, we can say that the limit of sequence n when n tends to infinity is equals to L. For every epsilon that belongs to the real numbers and it is greater than 0, that is to say for every positive epsilon, as small as we would like, there exists capital N that belongs to the natural numbers, and for every n that is a natural number, for every n that is greater than capital N, we will get that the absolute value of an minus the limit L is less than epsilon. Okay? So here, if L is the limit of sequence an when n tends to infinity, then here L is at this point. So the environment of the limit L starts from L minus epsilon, and the point L minus epsilon is not included in the environment of L, and ends at the point of L plus epsilon. And L plus epsilon, the point L plus epsilon is not included in the environment of L. And the radius of the environment of L is epsilon. And in order that a sequence an will have a limit n, most of the terms of sequence an must be located in the environment of L. That is to say, most of the sequence of an must be located between those two brackets. So they are located from L here, from L minus epsilon until point L plus epsilon. Only if most of the terms of the sequence an will be located inside those two brackets, sequence an, the limit of sequence an when n tends to infinity will be equal to L. And until the index n, we have fixed terms that are not located in the environment of L, but from the index n onwards, we have infinite terms that are located in the environment of L. Because of the fact that we have infinite terms that are located in the environment of L, that is to say between those two brackets, for that reason the limit of sequence an and n tends to infinity equals to L. Okay? And we know that inside those two brackets, each term that is located inside those two brackets the distance of each term from the limit L is up to epsilon. Okay, no matter where the term is located, as long as is located inside those two brackets, the distance of the term from the limit L will be up to epsilon. Okay, so symbolically you can write down that the condition that must hold in order that the limit of sequence an when n tends to infinity will be equal to L as follows. For each epsilon that belongs to the real numbers and it is a positive, for each epsilon as small as we would like, there exists capital N that belongs to the natural numbers. So for every n, for every natural n, for every n that is greater than, for every natural n that is greater than capital N, we will get that the absolute value of an minus the limit L is less than epsilon. Okay. Then I presented to you an example of a sequence an that is equal to 1 over n, that its limit when n tends to infinity is equal to 0. Here, when the index n equals to 1, the value of the first term is 1 over 1, when the index n equals to 2, the value of the second term is 1 over 2. When the index n equals to 3, the value of the third term, sequence an equals to 1 over n, is 1 over 3. When the index n equals to 100, the value of the 100th term is 1 over 100. So it is very easy to see that as n increases, the terms of the sequence are getting closer and closer to 0. Therefore, we can assume that the limit of sequence an equals to 1 over n when n tends to infinity is equals to 0. So in order to prove that the limit is indeed equals to 0, we have to prove that this condition holds. Okay? So we will prove that the condition holds. The condition that must hold is as follows. Let epsilon be greater than 0 and as small as we would like. So for this epsilon, there exists capital N that belongs to the natural numbers. So for capital N that is big enough, we'll get that for every natural number n that is greater than capital N, we'll get that the absolute value of 1 over n minus the limit 0 is less than epsilon. So that is the condition that must hold in order that the limit of sequence an equals to 1 over n when n tends to infinity will be equal to 0. So we prove that this condition indeed holds. The absolute value of 1 over n minus 0 is equal to 1, and the absolute value of 1 over n, because when you subtract 0, it doesn't change anything. So we can cancel the 0 here. And because of the fact that n is a natural number, then 1 over any natural number is a positive number. And we know that the absolute value of a positive number equals to the positive number itself. That is to say, the absolute value of 1 over n that is a positive number equals to 1 over n. And we have to prove that 1 over n is less than epsilon. Okay? So we have to prove that this inequality is true. Inequality is 1 over n is less than epsilon. Here we multiplied this inequality by n, and we got that 1 is smaller than epsilon times n. Then we divided this inequality by epsilon, and we found out that 1 over epsilon is less than n. Okay? So n must be greater than 1 over epsilon in order that this condition will be true. N must be greater than 1 over epsilon. And we have the right to choose any capital N that we want. So we'll choose capital N that is greater than 1 over epsilon. Therefore, for any n that is greater than capital N, and we choose capital N that is greater than 1 over epsilon, so from this inequality, n is greater than capital N that is greater than 1 over epsilon, we can derive that n is greater than 1 over epsilon. That is to say, if we choose capital N that is greater than 1 over epsilon, then the condition that must hold, this condition indeed holds. Yeah? So we have to choose capital N that is greater than 1 over epsilon in order that this condition will hold. Okay? So we will choose n that is greater than capital N. So this condition and this inequality is true according to our selection. Okay? Here we divided this inequality by n, and we got that 1 is smaller, 1 is bigger than capital N over n. We divided this inequality by capital N, and we got that 1 over capital N is greater than 1 over n. So this inequality is true because we choose n that is greater than capital N. And we have already proved that the absolute value of 1 over n minus the limit 0 is equal to the absolute value of 1 over n, and the absolute value of 1 over n is equal to 1 over n. And we have already proved here that 1 over n is smaller than 1 over capital N, so we can write down this inequality here. And we choose capital N. We choose capital N that is greater than 1 over epsilon. Okay? Or 1 over epsilon is smaller than capital N according to our selection. Okay? So here we have 1 over epsilon that is smaller than capital N. In the numerator, we have 1 in both expressions. So here, the denominator of this expression is smaller than the denominator of this expression, and the numerator in both expressions is the same, it is 1. So actually, when you decrease the value of the denominator, the number increases. Like here, if we have the expression 1 over 5, in the denominator we have 1. If we decrease in the numerator we have 1, here in the denominator we have 5. So if we decrease the value of the denominator from 5 to 4, the number itself, 1 over 4, will be greater than the original number 1 over 5. That is to say, when you decrease the denominator from 5 to 4, the number itself, 1 over 4, will be greater than the original number, 1 over 5. So here we decrease the denominator from capital N to 1 over epsilon, and therefore the expression itself will be greater than the original expression. Okay, therefore 1 over epsilon is greater than 1 over capital N. Okay, and what is the value of 1 over epsilon? It is equal to epsilon. So, in conclusion, we found out that the absolute value of 1 over n minus the limit 0 is less than epsilon. That is to say, if we choose the natural number n that is greater than 1 over epsilon, then we'll get that n, for every n that is greater than n, and n is for every n that is greater than capital N, and capital N is greater than 1 over epsilon. From this inequality, we can derive that n is greater than 1 over epsilon, and that is the condition that must hold. Here, n must be greater than 1 over epsilon. So if we choose capital N that is greater than 1 over epsilon, we will get indeed that the condition holds. That is to say, n is indeed greater than 1 over epsilon. And that is to say, we will get that the absolute value of 1 over n minus 0 is less than epsilon. Okay, so we actually proved that the condition that must hold in order that the limit of sequence an equals to 1 over n when n tends to infinity will be equal to 0 indeed holds, and for that reason the limit of sequence an equals to 1 over n when n tends to infinity is indeed equals to 0. Okay, so we finished to talk about the sequences that has a finite limits. In the next step, we actually talked about sequences that have infinite limits. Okay? So here we write down that the limit of sequence an when n tends to infinity will be equal to plus infinity. In this way, we can write down the same thing also according to the second method, an with the right arrow equals to plus infinity. Those are the two ways to write down the same thing, that the limit of sequence an when n tends to infinity is equal to plus infinity. So the following condition must hold in order that the limit of sequence an when n tends to infinity will be equal to plus infinity. The condition that must hold is for every k as large as we want, k belongs to the real numbers. That is to say, k could be any real number that we would like. There exists capital N that also belongs to the natural numbers. So for every natural number n that is greater than capital N, we will get that an is greater than k. Okay? So that is the condition that must hold in order that the limit of sequence an when n tends to infinity will be equal to plus infinity. So symbolically, we can write down the condition that must hold in order that the limit of sequence an when n tends to infinity will be equal to plus infinity as follows. For every k as large as we want that belongs to the real numbers, there exists, this is the sign of exists, there exists the natural number n, such for every natural number n that is greater than capital N, we will get that an is greater than k. So here, until the index n, we have fixed terms that are not obeyed to this condition, but from the index n onwards, we have infinite terms of sequence an that are greater than k. And because of the fact that we have infinite terms of sequence an that are greater than k, that is the reason that the limit of sequence an when n tends to infinity will be equal to plus infinity. Okay? Then I presented to you an example for the limit of the set of the natural numbers. So the limit in the broadest sense of the natural numbers is equals to plus infinity. We can present the natural numbers according to the formula that an equals to n. If the index n equals to 1, then a1 equals to 1. If the index n equals to 2, then a2 equals to 2. If the index n equals to 3, then a3 equals to 3. And if the index n equals to 100, then a100 equals to 100, etc., etc. If the index n equals to n, then an equals to n. So you can see, it is very easy to see that when the index n increases, the terms of the set of the natural numbers are also increasing. Therefore, we can assume that the limit in the broadest sense of the natural numbers when n tends to infinity is equals to plus infinity. Okay, the condition that must hold in order that the limit of the set of the natural numbers when n tends to infinity will be equal to plus infinity is as follows. For every k as large as we want, there exists the natural number n. So for every, there exists the natural number capital N. So for every n that is greater than capital N, we will get that an is greater than k. Okay? So in order that this condition will hold, we will choose capital N that is that is equal to the integer value of k plus 1000 when it is rounded up. Okay? And we know that an equals to n. That is the way that we present the terms of the natural numbers. So an equals to n. So for every n that is greater than capital N, and according to our selection, capital N equals to the integer value of k plus 1000 when it is rounded up. So from this inequality, we can derive that an is greater than the integer value of k plus 1000 when it is rounded up. And if an is greater than the integer value of k plus 1000 when it is rounded up, let alone that an is greater than k. Okay? That is to say, we proved that the condition that must hold in order that the limit of the natural numbers in the broadest sense when n tends to infinity will be equal to plus infinity indeed holds. And for that reason, the limit of the natural numbers, that is to say the limit of an equals to n when n tends to infinity equals to plus infinity. Okay? And we have also sequences that have the limit in the broadest sense to minus infinity when n tends to infinity. Okay, we can write down in two different ways that the limit of sequence an when n tends to infinity is equals to minus infinity. So only if the following condition holds, the limit of sequence an when n tends to infinity will be equal to minus infinity. The condition that must hold is as follows. For every k as small as we would like, k belongs to the real numbers. For every real number as small as we would like, there exists capital N that belongs to the natural numbers. So for every natural number n that is greater than capital N, we will get that an is smaller than k. So until the index n, we have fixed terms. So we have maybe fixed terms that are not obey to this condition. But from the index k, from the index n onwards, we have infinite terms that they are all smaller than k. And because of the fact that we have infinite terms in sequence an that are smaller than k, and k is any small number as small as we would like, For that reason, the limit of sequence an when n tends to infinity equals to minus infinity. So symbolically, you can write down that condition that must hold in order that the limit of sequence an when n tends to infinity will be equal to minus infinity as follows. For every k as small as we would like, k belongs to the real numbers, there exists capital N that belongs to the natural numbers. So for every natural number n that is greater than capital N, we will get that an is smaller than k. I'll repeat again that there may be fixed terms until the index n. We have fixed terms of sequence an that don't obey to this rule, but from the index n onwards, we have infinite terms of sequence an that obey to this rule. They are smaller than k. And for that reason, we can say that the limit of sequence an when n tends to infinity equals to minus infinity. So the limit is in the broadest sense. Okay? Then we talked about the arithmetic of limits. So if the limit of sequence an when n tends to infinity exists, and the limit of sequence bn when n tends to infinity also exists, then the limit of sequence an plus bn when n tends to infinity equals to the limit of an when n tends to infinity plus the limit of sequence bn when n tends to infinity. Question number 2, it is also true that the limit of sequence an minus bn when n tends to infinity equals to the limit of sequence an when n tends to infinity minus the limit of sequence bn when n tends to infinity. And we have a question number 3 that is also true. According to equation number 3, the limit of sequence c times an when n tends to infinity equals to c times the limit of an when n tends to infinity. C belongs to the real numbers. That is to say, C could be any real number. And equation number 4 is also true. The limit of sequence an times bn when n tends to infinity equals to the limit of sequence an when n tends to infinity times the limit of sequence bn when n tends to infinity. We have also equation number 5 that is true. According to equation number 5, the limit of sequence an over bn when n tends to infinity equals to the limit of sequence an when n tends to infinity over the limit of sequence bn when n tends to infinity. Here, because of the fact that this expression, the limit of sequence bn when n tends to infinity, is located in the denominator of this expression, it must not be equal to 0. Why? Because we it is not allowable to divide anything by 0. For that reason, the limit of sequence bn when n tends to infinity must not equal to 0. And finally, we have a question number 6 that is also true. The limit of sequence an to the power of p when n tends to infinity equals to the limit of sequence an when n tends to infinity, and we will raise the result that we will get here, that is the limit of sequence an when n tends to infinity to the power of p, and the final result here must be equal to the limit of sequence an to the power of p when n tends to infinity. Okay, thank you very much.